Alright, hi everyone. This is going to be a video lesson on section 3.5, the laws of sines and cosines. Now, if you were at our last class, we actually did the first 2 pages of this section. But, since we're going to talk about the rest of it, and since it's been a few days, I decided I'm going to go ahead and do a quick recap of the first 2 pages before we get to the new stuff. So, I'm not going to go through in it as much detail as we did last time, but this is about solving a triangle, and remember that means finding everything there is to find out about the triangle when you're given some of the information. One thing we said is that this is a common way to label a triangle. So the side lengths are lowercase a, b, c, and the angles are uppercase a, b, c, and they're labeled in this particular way where lowercase a is directly opposite from uppercase a, and the same is true for the B's, and the same is true for the C's. So they're not just labeled randomly, they're labeled that way on purpose. That's going to be sort of our standard way of labeling a triangle. And it says, how can we solve a triangle that's not a right triangle? And the idea is that we can't use the Pythagorean theorem, and we can't use the trigonometric ratios, like things like sine equals opposite over hypotenuse. You can't use things like that when it's not a right triangle. So that brought us to the law of sines, and I'll write the formula here. We said this in class, but here it is. It's a really nice formula. It has all 3 side lengths and all 3 angles in one big equation, showing how all 6 of these things relate to each other. And the idea is that if we know some of these, then we could use the equation to find the missing ones. And we have to have enough information. We can't just solve a triangle with nothing, but we're going to see some problems where you have some of these pieces and you need to find the others. And I'll skip writing the why is this true, but we did that in class, and it basically comes from the area formula for a triangle. All right, so let's make sure we know this formula. And we did example 1, so I'm not going to do every step of it, but I'll do a quick recap. Let's see. But yeah, I believe this was the last thing that we did in class. So, first of all, the sum of all 3 angles must be 180 degrees. So you can always use that for any triangle. And we used that to find that angle B must be 135 degrees. And I'm calling, that's angle B, the one with the uppercase B here, and that's the missing angle, and we know the 20 and the 25, so in order to add up to 180, that had to be 135. Then we used the law of sines, which for this triangle looks like this. It's good that we had the 135 already. So if you can get something like that first, it's good to do that. All right. We set it up like this, and our goal is to find lowercase a and lowercase b. I think in class we grabbed this part of the equation and worked with this. So when you have a fraction equal to a fraction, you can cross multiply, take, upper left times lower right, equals lower left times upper right, and we used this. I'm going to skip some of the steps, but we skipped, we'll skip a couple of steps here, but we used this to find that B was around 134.5. And then we used law of sines again to find lowercase a. Right, so this is taking the other part from the law of sines. The sine 20 over a equals either one of these things. You could use either one. And from this, we found that a was around 65.1. All right, and then you can summarize your answer by giving all 6 pieces of information, the angles, and the side lengths, all in one place, and label them so that we know which one is which. And notice that in this entire page, like I said, I was skipping a couple of steps because we saw this problem already. Just wanted to do a quick recap. But notice that in this entire page, we never said anything about a hypotenuse. There's really no such thing as a hypotenuse unless it's a right triangle. So we don't use anything like that, and we don't use the Pythagorean theorem. The law of sines is what we used. All right, so now we can get to the new stuff. So something a little different is going to happen in example 2. All right, let's see. First of all, there's no picture given. It's describing a triangle. Well, we'll say that it's labeled in that standard labeling we saw a couple of pages ago. Because there's no picture given, I think it would be a good idea for us to draw one. And when you draw a triangle to go along with a picture, it doesn't have to be perfectly to scale. It's really just to organize the information, to have the 3 sides, to have the 3 angles. So why don't I just, pick a point, and I'll say this is A, and let's see. One of the sides is 7, one of the sides is 7 times the square root of 2. Here's what I'm thinking. I know what a 45-degree angle looks like. Let's say a 45-degree angle looks something like that. I'll go ahead and label 45 degrees. So the side length that is opposite from this is lowercase a. And then one of the other sides, whichever one we choose, is going to be labeled lowercase b. So why don't I say that this one is the lowercase b, which is given as 7. And now, when I draw my lowercase a, like I said, it doesn't have to be perfectly to scale, but I am going to ask myself which one of these should look longer. And I think 7 square root of 2, that must be the longer one. Square root of 2, even if you don't know exactly what it is, you know it's 1 point something. It turns out that it's around 1.4. So 7 times 1.4 is bigger than 7. So I'll just try to make this side look longer, and it also has to meet up with the other side, so I'll say it's something like this. By the way, apologies if I have a little bit of a sore throat, but I think we'll get through this. Okay, so, like I said, doesn't have to be perfect, but this is helping us organize all the information. All right, so let's see. We only have one of the angles given. This angle C in my picture looks like it might be 90 degrees, but we can't really assume that. So let's just keep going, and we won't assume that that is or isn't 90. Let's use the law of sines. And by the way, I think we need all of the space on this page because some things are going to happen, so we're going to probably fill this entire space with notes. Let's see. We want to find the missing pieces. I don't think we can really go after C right now because we don't know lowercase c or uppercase c. I think going after that part would be tough. Let's use the other part of the law of sines and try to find uppercase b. If I cross multiply, it looks like this. Right, that looks good so far. And then solve for sine b. 7 over 7 square root of 2 times sine 45 degrees. All right, luckily 45 degrees is one of our common angles, so we could work with this. Also, those 7s cancel out. I have a 7 over 7, so I'll just make that a 1. And sine of 45 degrees is the square root of 2 over 2. So I canceled 7s. I'll go ahead and cross them out. And I can cancel those square root of 2s. So this is 1/2. So what did we find? We found sine of b equals 1/2. And we want to know what is b. You could put the little angle symbol before b if you want to. But yeah, we're looking for the angle b in degrees. Now, looking at this question, right? Sine b equals 1/2. What is b? it makes me think we've seen questions like that before when we talked about inverse trig. But there's something I need to tell you. So the note that I want to tell you is don't just use inverse sine. It's tempting to just say, oh, it must be inverse sine of 1/2, right? But here's the issue. Inverse sine has a range of negative pi over 2 to positive pi over 2, which is, in degrees, negative 90 degrees to positive 90 degrees. Now, an angle for a triangle must be within, what do you think? I mean, think about what's the smallest that an angle could be, or what's the largest that an angle could be in a triangle. Let's say between 0 and 180. I don't think this is going to be quite that large, but for any triangle, for any angle in a triangle, it must be in that range, right? So there's kind of a mismatch here. This is why I'm going to say don't just use inverse sine, because these intervals are not the same. And that can sometimes cause issues. Now, if we want to find b, and I'm telling us not to just blindly use inverse sine, then what do we do? Well, we still want to answer this question, right? That's what we know about b. We want to know what is that angle, preferably in degrees. Let's go back to what we know about the unit circle. That's not a very good circle, but it's good enough. On the unit circle, I know some places where sine of an angle equals 1/2. I could think of 2 places. And those 2 places on the unit circle, I know that sine of 30 degrees is 1/2. And I know the other one is sine of 150. I mean, we kind of knew that in radians, but in degrees, it's 150. So then the question becomes, which one of these 2 angles is it? Is it 30 or is it 150? So is angle B 30 degrees or is angle B 150 degrees? So we're going to kind of use logic to figure out which one of these it has to be. This is the part where if we were meeting in person, if we were in the classroom right now, I would ask someone to tell me. So why don't you just think about it for a second? All right, so what I want to say is it can't be 150 degrees. And you could think about how we know that. It's because the angle A is 45 degrees. And we know that all 3 angles added together have to be 180. So we can't really have a 150 degree angle in this triangle because it would put us over budget. It would put us over 180 already. So what we can conclude is that this has to be 30 degrees. All right, so this whole kind of discussion here, I said we don't want to just use inverse sine. We want to kind of figure out what are the possible options and then see if we can use some kind of reasoning to figure out which one is correct. In this case, it was the 30 degrees. And then to finish off this problem, let's see. Figure out what else do we need from this triangle. We could go ahead and find angle C. Looking at the picture, we know angle A, we know angle B. So they need to add up to 180. So we could do something like this. Let's say angle C must be 105 degrees, and that's to get all 3 of them to add up to 180. And then I guess we should use the law of sines again to find lowercase c. All right, we don't have a ton of space here, but we'll make it work. Using this from the law of sines that we wrote up at the top, and we're going to get lowercase c from this. So cross multiply. And c equals 7 square root of 2 divided by... So I'm dividing by sine 45 degrees. I know that that's the square root of 2 over 2. We could do a little canceling here. I guess this would be 14 sine 105. So I did a little simplifying of canceling the square root of 2's, and then instead of dividing by 1 over 2, I multiplied by the reciprocal. So 7 times 2 got me 14. Sine of 105 degrees, that's not one of our common angles, so I did kind of use a calculator at the end here. I found this is around 13.5. And I could go back to my picture and ask myself if this makes sense, but then you also have to keep in mind that we don't know if that picture was totally accurate or not, so I don't know. Maybe use that as a rough guide if you want and say, yeah, I think that seems reasonable. Anyway, we found all the solutions. I guess answers... You know what? Since I don't have much space, I'm just going to list the part of the answer that we found, the part that wasn't actually given. We found those two angles and this side length. All right, so I didn't list the 3 pieces that were already given in the problem. All right, so what happened in this problem that was different? Number 1, we weren't given a picture, so we drew a picture ourselves. And then number 2, it was this whole business about inverse sine. So some of that is typed up here. That sometimes there seem to be 2 choices for an angle, but only one of them makes sense. So that happened here with the 30 and the 150. Only the 30 degrees made sense for this triangle. But then it goes on to tell us sometimes both are valid and the problem has 2 solutions. So that's interesting. You know, if you get to a step like this in a problem and neither of these angles have any problem, then maybe they both work, and then you kind of have 2 possible triangles that could be solutions. And then it also says sometimes there are no solutions. So that I think we might see one of those later in this section. Let me see. Do I have an example like that? Yeah, I'll show you one of those. All right, so let's go to the next page and see what kind of case this is. Well, this one doesn't give us a picture. It also doesn't give us much space, so I'm going to sort of spoil the answer to this and tell you this is going to be one of those ones where there's no solution. I'll start this out, and let's see what happens to indicate that there's no solution. We could just jump right into the law of sines and say sine of 60 degrees over 80 equals sine of b over 160 equals sine of c over c. So I guess what you would do is you would take these 2 parts and you would say, oh, well, maybe we'll be able to solve for uppercase b, cross multiply. So everything looks normal so far. But I want to show you what is about to happen. So we would try to solve for sine b. So we get sine b equals, divide both sides by 80. So 160 over 80 is 2. So 2 times sine 60. So sine of b is 2 times, you can figure out what sine of 60 degrees is. You could think about the unit circle if you need to. That's square root of 3 over 2. So sine of b is the square root of 3. All right, well, here's the issue. What angle B is going to make this happen? Well, this never happens. There is no angle that has a sine of it equal to square root of 3. Square root of 3, by the way, is approximately 1.7. Not exactly, but approximately 1.7. That's too big. That's larger than 1. And even if you don't remember that this is 1.7, you can tell that this must be larger than 1, right? Think the square root of 4 is 2. The square root of 3 must be 1 point something. And sine can't get that large. Sine can't get bigger than 1. So all you would do is you would just say no solution, or does not exist. There is no triangle that solves this problem. All right, so we have another question. Can we still solve a triangle if we're not given any angle measurements? So this one is giving us 3 sides. It's giving us all 3 sides, but none of the angles are labeled at all. So I have a little spot for notes here. And the note that I want to tell you is that the law of sines doesn't help here. And I'll show you why. If we try the law of sines, well, let's see, what does it look like? Sine A over 5 is sine B over 8 is sine C over 12. So do you see why I'm saying this doesn't help, that we're kind of at a dead end? Normally, with the law of sines, you would grab part of this and maybe cross-multiply to try to solve for something. But the problem is, because we don't know any of the numerators, we can't really pick any part of this to solve for something. Because if you pick the left piece and the middle piece, you would have 2 unknowns. Or if you pick the middle and the right, you would have 2 unknowns. Or if you pick the left and right, there's nothing we could do to solve for A or B or C just using this information. And that is why we have another formula, the law of cosines. So for this situation and a couple of others, there's another formula. And it's actually kind of 3 formulas in one. So I think what I want to do is write the formulas here, and then a little later we'll talk about where they come from. All right, let me go ahead and write them first. So we're going to have 3 formulas stacked on top of each other, and they all have kind of a similar structure, similar form. All right, as you would expect, these ones have a cosine in them instead of a sine. All right, let's put a big box around this. Altogether, these are called the law of cosines. So take a moment and copy that if you need to. All right, so before we solve a problem with this, I'll tell you, the plan is we're going to solve a problem with it, and then a little later we'll talk about where does this come from. But we're already seeing the reason why we needed a new formula is that the law of cosines, or the law of sines, wasn't enough. We needed something else. Before we do any of that, I just want us to maybe look at this and see, is there anything in this that could maybe help us remember it? I do notice that all 3 of these kind of have this same layout. You know, this one starts with an a squared on the left, and the angle that we're working with is uppercase A. This one starts with a b squared, and the angle that it works with is uppercase B, right? And then this one works with C. So there's kind of an A version, a B version, and a C version. And you could use any of them, and maybe the one that we'll use depends on what the problem looks like. But my idea is that if you could remember one of these, then maybe you can figure out the others from it, because they all have this same kind of layout. One thing that I kind of like is the third one. If you look at the bottom one, c squared equals a squared plus b squared minus something. I noticed that it almost looks like the Pythagorean theorem. I just want to put a little side note here. Do you remember the Pythagorean theorem for right triangles? Is a squared plus b squared equals c squared. This is just a little side note. But I don't know. I feel like there is a connection here. We said that the Pythagorean theorem only works for right triangles. And in this section, when we draw triangles, we're not assuming that they are right triangles. So the Pythagorean theorem doesn't apply. But the law of cosines, at least the third form of it, almost looks like the Pythagorean theorem, because I have an a squared plus a b squared. I have it equals a c squared, except there's this other term. So it's almost like saying the Pythagorean theorem doesn't apply because there's this much extra. It's like the Pythagorean theorem is off by this amount. I don't know if that helps you remember it or not, but I think that the a squared plus b squared equals c squared, it's kind of like it's embedded within the law of cosines. I don't know. Maybe that's a little side note, but you can notice that the two letters that are used here are the two letters that are used here, right? AB, AB. This is an AC, AC, BC, BC. So yeah, they all have the same kind of structure. All right, let's look at a problem. All right, so the law of cosines is a little trickier to remember. It's not quite as nice as the law of sines, but we need it sometimes. So we'll solve this triangle. This is the one from the previous page. So, we want the angles, right? We want A, B, and C. And I'm already thinking if I could find two of them, then we would get the third one really quickly, because we could just say they all have to add up to 180. So if we find any two of them, we'll use that as a shortcut to find the third. All right, let's try this. This was the first form of the law of cosines, and let's see what happens. Now, if I want to find uppercase A, we should be able to find uppercase A from this, because think about it. We know lowercase a, lowercase b, lowercase c. We know everything in this equation except for one piece, so we should be able to solve for it. Now, we could plug in the 5, the 8, and the 12, and then solve for A, or we could start rearranging first. I think I'm going to start rearranging first. It's actually up to you. Do you want to plug in the 5, 8, and 12 first, or do you want to do some rearranging first? But I chose to do it this way. Okay, so I sort of got cosine A by itself, everything else on the other side, and now I'll put in the numbers, the 8, 12, and 5. Well, you can do a little scratch work off to the side if you need to. I wound up finding that this is 183 over 192. Kind of a weird fraction. So cosine of A is this fraction. That's definitely not one of our common angles. But what we're going to say then is that... Here, I'll just copy this to make sure we have it. Okay, I just wanted to copy that. What we can actually say is angle A does equal inverse cosine of that fraction. And I found this with a calculator to be around 18 degrees. So there is a note at the bottom of the page that we're going to get to in a moment. We're not really done with this problem yet because we still need to find B and C. But I guess I should address this part now. It is okay to just use inverse cosine here. All right, so if you take a quick glance at the note at the bottom of the page, that's what it says. Let's find B and C. I'll say similarly, if we do the law of cosines and try to find B, and you could try that if you'd like. You know, in videos like this, at any point, you could always pause and try steps on your own. This gets us 105 over 120. Now, that fraction actually does simplify. I look at that and I say, oh, well, they're both divisible by 5. Maybe they're both divisible by something else. They're both divisible by 15, in fact. So this simplifies to 7 over 8. And angle B is inverse cosine of 7 over 8. That winds up being around 29 degrees. And finally, for the angle C, we could use the law of cosines again. We could use the third form of the law of cosines, but that would be overkill. We don't really need to. We could just say all three angles have to add up to 180. We have an 18 and a 29. So 180 minus 18 minus 29 should get 133 degrees. All right, so the solution, I think I have space here, so I'll try to write all three angles and all three sides. Angle A, we found, I'll say we rounded off. This is close enough. All right, now let's take a closer look at that note at the bottom. So you may have looked at this in the middle of the problem, but yeah, when we use the law of sines, I said we should not just automatically use inverse sine because of the issue with the range. But for the law of cosines, it is okay to always just use inverse cosine because its range does match up with all possible angles in a triangle. So, yeah, we never get that situation where there are two solutions to choose from. So the law of cosines is a trickier formula, but I guess the one good piece about it is you'd never have that complicated situation with two solutions. So I think a question that could happen right now is, how do we know which rule to use? Like, when do I use the law of sines? When do I use the law of cosines? Can I use either one? So next page, we'll discuss that. So page 119 starts with some guidelines, and there's a little space for us to fill this in. But yeah, we're going to say that there are 4 possible cases, depending on what information you're given. If you're given one side and 2 angles, or if you're given 2 sides, or if you're given 3 sides. That was the one we just did, by the way, case 4, where you're given all 3 side lengths. And you know that we just used law of cosines, so you're thinking case 4 is probably law of cosines. So in general, the suggestion is law of sines for cases 1 and 2. Law of cosines for cases 3 and 4. Now, I'm calling this guidelines, and I used the word suggested. The truth is, you might want to experiment with a problem to see what works. You know, something you might do is you might use a combination of both laws. Like, you might start off a problem using the law of cosines, and then once you find some kind of side or angle, now you have enough information that maybe you could switch to using the law of sines to finish it. You know, you find part of the triangle using one law and find another part of the triangle using the other law. So there's some flexibility there if you want to just experiment and see what works. All right, so I think I would like to have you try example 5. If we were in class, I would give you a few minutes to do this. Since this is a video, I'm going to suggest that you pause the video and give this a try. So I'm going to help out here, and maybe you paused it and tried it. I think that the law of cosines is the way to go, and we need to find a, so let's use the law of cosines that has an a squared on the left. Okay, and this is what's called case 3 up at the top of the page, because we have an angle and the two sides around it. So we're just trying to find lowercase a here. Let's plug in everything that we know. Looks like that. So a squared equals 16 plus 25 minus, multiply that out, you should get 40. (16 plus 25 is 41. Cosine of 30 degrees, you can find that. That's square root of 3 over 2. Be a little careful with this 41 minus 40 that you're seeing here. I know it's tempting to subtract those, but we have to remember order of operations says this 40 times this number happens first. So don't subtract 41 minus 40. That would be an order of operations mistake. The 40 is attached. You could even do parentheses if you want. The 40 is attached to this. But we could do the 40 over 2. We could do that. So a squared equals 41 minus 20, square root of 3. How about that? And that was a squared, but what we really wanted was a. So we would do the square root of both sides. And, in math, when you do a square root of both sides, you think there should be a plus or a minus symbol. But we don't need the plus or minus symbol here, because I know that a must be positive. Look at this. It's a side length in this triangle. I know it's a positive number. So don't write plus or minus. It is just the positive. And yeah, big square root around this number. That's it. That is the answer. It's a weird looking number, but that is a. So you'll sometimes get weird-looking answers like that, especially with the law of cosines. I'll tell you, I did find this with a calculator, just in case we're curious. This is around 2.52, and then I'll just say, in the picture, that kind of makes sense. It looks like A was the smallest side length. But we don't even need that. The one that we put a box around is the exact answer. All right, so we're almost done here. I'd like to take a quick look at the next page, page 120. I wanted to talk a little bit about why is the law of cosines true. So at the beginning of the section, we saw that the law of sines came from the area formula for a triangle, and this goes over where the law of cosines comes from. So just real quick, it's already typed for us, but if you have an angle A in standard position and all the points are labeled as shown, this suggests that we try to find the side length A. So the side length A could be found by using the distance formula, where you're looking for the distance between the points C, 0 and this point up here, right? The other point was just labeled the origin. That's what makes it standard position. A was located at the origin. So anyway, the distance formula between these 2 points looks like this, all right? And then it's suggested that in order to make it look more like the law of cosines, which is what we're trying to show is true, you would square both sides. So it's suggested that you try it, that you could square both sides and simplify, and it does, in fact, turn into the law of cosines. And the other two versions of it can be found using the same kind of strategy. So I'm not really going to make you do this from scratch. That's not really the point of this. The point of this is just so we're a little bit more justified in using this, that we've seen where it comes from. And the general idea is the law of sines is true because of the area formula, and the law of cosines is true because of the distance formula. All right, so a lot of times in math, new formulas come from old ones, and everything in math kind of builds upon previous things. All right, so I think we'll say that's enough for this section, but as always, you can look at the practice exercises on the next page. I'll save those for you to look at on your own, and those have the answers in the back of the workbook. All right, so that's it, and feel free to let me know if you have any questions.